Let's explore the fundamental concepts of eigenvalues and eigenvectors in linear algebra. Eigenvectors are special vectors that only get scaled when transformed by a matrix, and eigenvalues tell us by how much. Let's start by understanding what an eigenvector actually is. An eigenvector is a special vector that maintains its direction when a linear transformation is applied to it. The fundamental equation is A times vector versus equals lambda times vector v, where A is our matrix. Here we see a vector v and its transformed version A versus notice they point in the same direction, just with different lengths. The key property is that the vector only gets stretched or shrunk, it never rotates to point in a different direction. Now let's understand eigenvalues and how they relate to eigenvectors. The eigenvalue lambda is simply the scaling factor that tells us how much the eigenvector gets stretched or compressed. Lambda represents the scaling factor in our transformation. In this example, the eigenvalue is 3, meaning the eigenvector gets stretched to 3 times its original length. When lambda is negative, the eigenvector flips to point in the opposite direction, while still maintaining the same line. Let's learn how to calculate eigenvalues from a matrix. Consider this simple 2x2 matrix A. We start with our eigenvalue equation. Rearranging, we get A versus minus lambda versus equals the 0 vector. Factoring out v, we get A minus lambda I times versus equals 0, where I is the identity matrix. For a non-trivial solution, the determinant of A minus lambda I must equal 0. Substituting our matrix, we get this determinant equation. Calculating the determinant gives us 3 minus lambda times 2 minus lambda equals 0. Solving this gives us 2 eigenvalues, lambda 1 equals 3 and lambda 2 equals 2. Once we have eigenvalues, we can find the corresponding eigenvectors. For each eigenvalue we found, we need to solve a system of equations to get the eigenvector. Let's find the eigenvector for lambda equals 3. We substitute lambda equals 3 into our equation. This gives us this system of equations to solve. From this we get versus 2 equals 0, and v1 can be any value. So our first eigenvector is 1, 0. Let's visualize how eigenvalues and eigenvectors work together in a transformation. Here we see 2 eigenvectors before transformation pointing in their special directions. After transformation, each eigenvector is scaled by its eigenvalue, but maintains its direction. Let's summarize the key differences between eigenvalues and eigenvectors. The eigenvector is a direction represented as a vector, while the eigenvalue is a scale represented as a scalar number. Think of it this way. The eigenvector tells you which direction. The eigenvalue tells you how much. Let's see a complete example putting everything together. Consider this matrix A. Setting up the characteristic equation and solving for lambda. This simplifies to lambda squared minus 7 lambda plus 10 equals 0. Solving gives us eigenvalues of 5 and 2. These eigenvalues tell us that one direction gets stretched by 5 times, another by 2 times. Let's recap what we learned about eigenvalues and eigenvectors. Eigenvectors are the special directions that remain unchanged when a matrix transformation is applied. Eigenvalues tell us by how much those special directions get stretched or compressed. Together, they satisfy this fundamental equation of linear algebra. Understanding eigenvalues and eigenvectors helps us understand the fundamental behavior of any linear transformation.